Hello, I'm Professor Johnson, and in this video we will be talking about the process of science. So first of all, let's talk about what science is. Science, simply put, is a way of knowing. It's a process that allows us to generate new knowledge about the natural world. There's really two major types of science. There's the observational science, which involves viewing, observing, sensing the world with your different senses, and measuring different things, quantitatively determining the size, the weight, the mass, etc. of different things. There's also the hypothesis-driven science. This is the science that we typically talk about when we're talking about the scientific method. So it involves making hypotheses, testing predictions, and really gaining insight to how things actually work and why they work the way that they do. Now, science is going to involve two different types of reasoning. It's going to involve deductive reasoning, where you're moving from general concepts to the specific, and then inductive reasoning, where you're moving from specific examples to a more general statement about the world. So the process of developing hypotheses is really going to use the inductive reasoning. So you're going to make several specific observations, and based on these observations, you're going to develop a general principle in which you want to test. So you may observe that cats have hair, cats are mammals, dogs have hair, dogs are mammals, iguanas don't have hair, iguanas are not mammals, and started coming to this conclusion that all mammals have hair. So that's the general concept that you come to. You also may look at the definition of mammal, something that produces milk to feed their young, and then observe that whales develop milk to feed their young, and then use deductive reasoning to conclude that whales are mammals. So in that case, you went from a general idea about what mammals are and identified a mammal based on that observation. Here you had several specific things that you used to generate a new hypothesis that you could then test. Inductive reasoning is not always ironclad in its reasoning. You can always come up with a new specific example that can throw your general hypothesis out so that you'd have to reform it. Deductive reasoning is always sound if it's performed correctly and the general principle that you started with is correct. If you started with faulty first logic in this, then the conclusions you come to via deductive reasoning won't necessarily be true. So let's take a look at the scientific method. You've probably seen the scientific method before, and you may have seen it displayed in a way that's either very similar to, but maybe different in some ways than what I'm going to show you. Regardless of how you've seen the scientific method, because there are different ways of displaying it, the idea of the scientific method is that it is a reiterative process, something that you're going to do over and over again to eventually develop your conclusions. So the scientific method should always start with either a question or observation. Observations will inform your questions, so you're going to make several observations that are going to lead you to developing a question, or you might have a question and go out and view different observations related to that question first. Regardless of what order you put those in, based on your question, based on your observation, you're going to come up with a hypothesis. So your hypothesis is a tentative explanation to the research question that you are developing. Your hypothesis is going to develop predictions that you can then test experimentally. Once you perform the experiments, you're going to have results of these experiments, and these results are going to lead to conclusions. Now, you really only have two different conclusions. You can either say that your hypothesis is supported or you can say that your hypothesis is not supported. If your hypothesis is not supported, you might want to go back then and test a new hypothesis. Now, notice that I did not say that your hypothesis is proven. With the scientific method and with science in general, you can never prove something absolute. There's always the possibility that new information will come along that forces you to reevaluate your hypothesis. The strength in the scientific method comes in when people repeat your experiment and find similar results, and when people repeat your experiment and don't find similar results, and when they come up with new information to test it. So the reiterative process allows you to gain more and more confidence in your conclusions. However, you will never be able to say that you have 100% proved a hypothesis. You can say, however, that you have refuted a hypothesis or disproved the hypothesis. An experiment, if performed correctly, that does not support the hypothesis will actually disprove that hypothesis. So let's go with just a simple example from everyday life. So let's say that you have observed that your remote control isn't turning on your television. You might start generating various hypotheses. Maybe the TV is unplugged, maybe the batteries in the remote are dead, maybe the remote is broken. All of those are good hypotheses based on previous observations. Sometimes TVs don't work when the remote is dead, or the batteries in the remote are dead. So all of these are good hypotheses that lead to predictions. Predictions such as, if we're going with the batteries in the remote example, that replacing the batteries will then make it so that the TV will function. So then you would perform your experiment and you'd get your results. Now your results would be either the remote started working and the TV now turns on, in which case your hypothesis would be supported, but maybe your hypothesis was not supported. Maybe the TV still won't turn on, in which case you might want to go back and test additional hypotheses. Notice that even though the remotes did change it, this doesn't prove your hypothesis. Maybe after you changed the batteries in your remote, you were at a different angle, and it was really the angle at which you were pointing the remote at the TV that mattered. Or maybe the batteries in the remote were just loose before, in which case readjusting them may have made it so that the remote then worked regardless of whether the batteries were changed or not. These are a couple of possible explanations of how you, even though your experiment was supported your hypothesis, it didn't necessarily prove that hypothesis outright. Now, you may have noticed that I made a distinction between the hypothesis and the prediction. It is not uncommon for some people to conflate these two ideas. So a scientific hypothesis does not need to be stated as an if-then statement. In fact, if your scientific hypothesis is stated as an if-then statement, it's usually not just the hypothesis that you're looking at, but other parts of the experiment. So note that the scientific hypothesis is a tentative answer to the research question that you're trying to answer. So your research question was, why won't the remote turn on the TV? If we look at a few of these different examples, if the TV won't turn on, then the batteries in the remote are dead. This is not a hypothesis. The hypothesis part of it is really the TV won't turn on because the batteries in the remote are dead. The if-then part of it did not need to be stated. The second one, if the batteries in the TV are dead, then changing them will fix the remote. So the first part is your hypothesis. The TV won't turn on because the batteries in the remote are dead. Then changing the batteries in the remote will then fix it so that it will work. So this is your prediction. Predictions generally will have a will. You do something and then this will happen. The last one is really your best example of a scientific hypothesis, the TV won't turn on because the batteries in the remote are dead. So hypotheses are really explanations about phenomena in the natural world, and it's your research question is trying to answer what is the deal with this, and your hypothesis then addresses that. All right, so in this class we're going to be looking at a number of different experiments, and as a science major you're going to be looking at a number of different experiments throughout your tenure as a scientist. And really you're going to be, as a human being, going to come across a lot of different experiments, either very tightly classical scientific experiments or more experiments like we talked about with the remote. Scientific experiments generally are going to have a number of features. So one thing that we look at with experiments are variables. So variables are different things in an experiment that can vary. So you may be looking at plant growth, and different variables would be the type of plant, the how much the plant's growing, the type of soil the plant's growing in, how much sunlight it's getting, how much water it's getting, etc. Now, there are two important variables that you are going to want to know about. There's the independent variable and the dependent variable. Now, the independent variable is the thing that is going to be manipulated in the experiment. So the independent variable is the thing that you are manipulating. So you may be, with the plants, wanting to know what the effect of different amounts of water are on the growth of the plant. So in this case, the different amounts of water that you give different plants is going to be your independent variable. Your dependent variable then is going to be the thing that you measure. So here it's going to be plant growth. So how I remember it is that the independent variable is the thing that I am changing. So I and independent both start with I. The dependent variable is the thing that you're going to measuring. So whether it changes or not depends on whether it is affected by the independent variable. Now, you may have other variables that you are going to want to control for. So when I say control, that means that you want to make these things the same in all of the experiments to make sure that the outcome you're measuring is a function of your independent variable. So these different things that can vary, such as the type of soil in this experiment, the type of plant in this experiment, the amount of sun in this experiment, these are things that you're going to want to keep the same. These are all confounding variables that you need to make sure remain the same in the experiment. Oftentimes, you're going to end up graphing an experiment. So when you graph an experiment, you are going to put the independent variable on the x-axis and the dependent variable on the y-axis. So in this graph here, I show the number of college classes taken as a function of your year in school. So freshmen aren't going to take as many college classes as sophomores will have, juniors, seniors, and then if you've gone beyond your senior year, you're going to have taken even more college classes. So in this case, the independent, the number variable, the number of college classes taken, was a function of your year in school. Now, there are a couple of specific experiments that you can have that are going to be important as well. So there are positive controls. These are experiments in which you know the outcome will have an effect. So a positive control could be, for example, with if you're trying to determine the amount of, or determine whether a substance contains protein or not, a mixture of protein, say whey protein, would be included in the experiment that will turn positive, will develop in showing that there is protein in there as a separate experiment from the one you are performing. Negative control experiments then are things where you know you won't get the result that should happen. So a negative control would be like distilled water. If you're testing for protein, it won't show up because there's no protein in that experiment. Positive and negative controls are included to show you that that your experiment is functioning as it should be. If you have a negative result in a positive control, this indicates that something was wrong with your experiment. And if you have a positive result in a negative control, this likely would tell you that there was something wrong with your experiment as well. So positive and negative controls help control or help show you when you have a false positive or false negative for experimental errors that you've had. Finally, looking at control groups versus test groups. So control groups are really your classic experiment. So in the plant example, the control group would be how much most people water plants. The test group then would be the different groups that receive different amounts of water. So there might be some plants that got less water and some plants that got more water. These would be your test groups. Control groups are there to show that it's actually the variable that you've been manipulating that's having an effect on the experiment. All right, so let's go through an example of the scientific process. So something that you may be wondering about and something that I'm concerned about as an educator is how can I better prepare students for exams, or how can students do better on exams? Exams are a measure of student learning and a large part of how we actually quantify how much learning you've had in classes. So a couple observations that have been made relative to this is that students who spend a lot of time rereading notes and the book, after you've read it, but continuing to reread it again and again, sort of passively hoping the information flows into your brain and sticks there. These students don't necessarily do great on exams. So they may study a lot, but they don't actually, that study doesn't seem to be benefiting them. However, others have observed that students who seem to quiz themselves over material covered in a lecture or in the book seem to do better on the material that they're actually quizzed on. So maybe after you've reread the book, you might close the book and you would quiz yourself, see if you can't write down a process that was being talked about, and then go back and open up the book and see how you actually did. Or sometimes doing the questions at the back of at the end of the chapter of a book would be another example of this. These students tend to do better on exams when this material that they've quizzed themselves over is better. So based on these observations, you might come up with the hypothesis that frequent quizzing over the material really stops the forgetting process. So your hypothesis, frequent quizzing over material stops the process of forgetting, generates several predictions. So one prediction is if students quiz themselves regularly, they will do better on exams. Another hypothesis is if a student or if an instructor includes more quizzes in their class, these low stakes don't necessarily count for points, or if they do, count for very little points, and the students then perform these and get feedback on them, then the students may actually do better on a final cumulative exam for that class. And then another prediction would be that in the same class, if the students are exposed to two different sets of material, one set of material they only read it and then maybe reread it, and the other set of material they actually quiz themselves on, your prediction would be, if your hypothesis is correct, that they would do better on the material that was reviewed by quizzing. Notice all of these predictions have will in them. So they will do better, they will do better, and they will do better. They're not all stated as an if-then statement, but they all make a prediction. Something will happen if you do something else. So let's look at one of these predictions. In the same class, if the students were exposed to material repeatedly via quizzing or rereading, then they will do better on exam material that was reviewed via quizzing. So we have two examples here. One is a quiz question that you might see, and another is just a statement. So you may be given a quiz over what a hypothesis is and suggest all that apply. And you may just read what a theory is. So a theory is a proposed explanation for a natural phenomenon, often based on some general principle. Now, if we have the students review this material by quizzing and this material by rereading, and then give a test, if our hypothesis is correct, you would expect them to do better on topics that were reviewed by quizzing than topics that were reviewed by rereading. This isn't just a hypothetical experiment, by the way. This has actually been performed, and students who actually quiz themselves over material tend to do better than students who just passively reread or rewatch or something the material that they're being quizzed on. Now, your hypothesis was supported. This doesn't mean that it's been proven, but you might then want to go back and look at different predictions. So you might want to test some of these other predictions with different experiments. This would allow you to have more and more confidence in your actual hypothesis. All right, that's it for this first video. I will see you in class where we'll do some activities that are related to the scientific process. See you then.